Okay, folks, this is section 5 of our notes. Talking about absolute value and absolute value inequalities. I think maybe it makes sense initially to talk about our absolute value uh, concepts real quick, and then we'll get into the structure with the inequalities. Okay. First thing we need to know about absolute value. Absolute value tells us the distance an object is from 0. Okay. Um, Something that you guys have talked about in previous courses would be this conditional statement, which is if, I'm just going to write a function inside here. So that could be anything. It could be 2x squared, could be 2x plus 5, could be x plus 3, whatever. It could just be x. If x is equal to c, then f of x is equal to c, or f of x equals the opposite of c. Okay? So this is a conditional statement that if our particular problem that we're working on looks like that, we can use what we call the law of detachment from geometry to allow us, for our specific problem, to generate this. Okay? Now, what does this mean to us? Well, think about this. If I am right here at 0, can I walk that direction to get to C? Let's say I walk C units to the right. Would this mean if I'm standing right here, would I be C units from 0? And then I think you can maybe make the argument that, well, that wasn't the only direction I could have walked. I could have walked that direction and be standing right there. The distance I would have walked would still been C units. But now, because I could have walked to the left instead of to the right, my coordinate, my location would be at negative C. And that's where this yellow stuff comes from. That's why we get two solutions for absolute value. Okay. Now, it says describe all values within or including that, or I should rephrase it. Describe all x values within or including that is a distance of 4 from 8. Well, think about that. A distance of 4 from 8. So let's say 8 is right there. A distance of 4 would mean I can go 4 units that way and put me at 12. Or I could go 4 units this way and it put me at 4. So all the values that are within a distance of 4 from 8 would be those values right there. Now it says or including, so when I write this in interval notation, I would write that as 4 with a bracket, 12 with a bracket. Okay. What this would mean then, what we'd actually be looking at, if we transfer this into math terms, is that we are looking for some x value that is less than or equal to, actually, let's write it this way. We'd be looking at something like this. What happens here, and I'll explain this all in great detail to you. The process for doing this would be to actually rewrite this way. Now if I solve for x, add 8 to all 3 parts, it gives me 12, 4 and 12. So that basically creates all of the x values that are 4 units from 8. Okay? So what this really says is find all of the x values that are going to be, again, 4 units, but 4 units from 3 in this case. When we're talking about absolute value inequalities, I'll come over here and just kind of give you some rules. If, let's see here, I have a hard time seeing my cursor. All right, so if absolute value of f of x is less than or equal to, or just less, let's just put just less than for now, less than c, then we write it this way. We say the opposite of c is less than f of x is less than c. And think what this means. It means the distance is less than c units from 0. Okay, well, if I'm looking at 0, then less than c units, if c is there, then that all that stuff that is green would be less than c units from 0. But remember, we can go over here as well. So then we would have all of these values being less than c units from 0. Well, if I look at everything that's highlighted here, and I basically say that all highlighted values are solutions, does it make sense that all my highlighted values are between negative c and c? And that's what this is it's a between statement. Here, it says if f of x is greater than c, then we write two things, right? F of x is greater than c, or f of x is less than negative c. Let's talk about what that picture would look like. Let's talk about what this says here. It's very similar to what I wrote up here. This here says the distance from 0 is more than c units. So if 0 is here, c is there, more than c units means I have to be beyond c. And that's what this would say. I mean, f of x is greater than c. That's what would be created right here that I've highlighted. But then we can also be over here to the left of negative c. And if I'm ever in anything that's green over here, I would be more than c units from 0. So let's say c was like 5, and this would be negative 5. Then if I'm at negative 7, does it make sense that I am more than c units or negative 5 units away from 0? Or if I'm at positive 7, I would be, again, more than c units or 5 units from 0. So that's why we have to have these two rules when it's a greater than. Okay. If it's greater than or equal to, less than or equal to, all that means then is that we have inclusion in our intervals. Okay. So just kind of knock out some examples here. The one thing that we have to remember is, and I'm going to write these because I think this is good because we never did this kind of thing before geometry, and I taught you then the law of detachment and the law of syllogism. And at that point, maybe that stuff kind of made sense and how we use those to make arguments about mathematics. But I think it's a lot more prevalent and obvious to use those laws or what those laws generate for us when we're working in algebra. So our two rules say if the absolute value of some expression, some function, is less than c, then we get f of x. We get this. We get negative c is less than f of x is less than c. And we also have one that says if f of x is greater than c, then f of x is greater than c, or f of x is less than negative c. So all we've got to do is say, okay, does this here match either of these hypotheses? And I think we recognize that it does. It matches this top one, right? So those two match. So then, because those two match, the law of detachment says for your specific problem, you can make this argument. Okay, so for my particular problem, x minus 3 is the f of x. So I put x minus 3 in the middle. My c is 4. So then I make it the opposite c, it's negative 4. Now we've got one of these these inequalities. This is a compound inequality. Treat it just like this, just like a normal equation. We've got to do this to all three parts now. So now I get negative 1 less than or equal to x less than or equal to 7. We talked a little bit about this last week, but this is, like a lot of times we would write it this way. We write it as x, and then this is the phrase such that, just shorthand for that two-word phrase. And then it tells us how x is identified as a solution. That's called set builder notation. It's what you guys are most familiar with. You probably didn't use ever in the bracket or the x such that part. Usually you guys just use that. But the formal way of writing it is with that bracket. But that's still kind of murky. That's more than what's necessary. So let's use interval notation. Interval notation, because that's equality. I'm going to have a bracket here on negative 1. Because that's equality, I'll have a bracket on 7. And that's a more concise way. Some of you on your quiz solved the inequality and then wrote your answer in that way. But in the instructions it says use interval notation. Okay, in this next example, we're still going to use this information up here. But now the argument or the question is, does the problem that I'm starting with match either of these hypotheses? Clean them up a little bit. Okay, so does this here match either of these? Okay, and my answer to this is going to be no, because if we look at the expression part, the absolute value part in both these, you see that they're isolated. They're by themselves. This absolute value bar down here, or a set of absolute value bars, is not isolated. And that's, if you go back to like Algebra 2, when you're taught this stuff, you maybe weren't taught to match to a true hypothesis like this. And your rules are probably in absolute value inequality to isolate, like step 1, isolate the absolute value bars. Well, why is that? Well, it's because of this. We're trying to match it to this. So to isolate these, we're going to subtract 1 from both sides, and then divide both sides by 2. Now that there matches that hypothesis. So if it matches that hypothesis, then for our particular problem, we can make this conclusion. So I can say my expression x minus 3 is going to be bigger than 2, or x minus 3 is less than negative 2. Add 3 to both sides here, so x is bigger than 5. Add 3 here, x is less than 1. Now, if I'm going to graph this, which I think is maybe beneficial to see a graph of these, I'm going to write the interval notation. If 5 is there, 1 is there, x is greater than 5 means that, x is less than 1 means that. Okay, so what we're looking at here is ultimately values here. If I think about this here, okay, any one of these values, like if I choose, let's say 6 out here, plug 6 in here, I get absolute value of 3 is greater than 2. Is that a true statement? Absolutely, it's true. If I try 0, because 0 is right there, I get 0 minus 3 is negative 3 in the absolute value. Is that greater than 2? Yes, it is. Any value I choose out here on these black rays is going to give me a true statement. Okay. If we make a kind of an argument about what we said right here, it says describe all x values within or including that is a distance of 4 from 8, and then remind ourselves of what that looked like. I think that example was like this here. I guess it was less than 4. Okay. So what this would say, if I'm looking at this, so this one was less than a distance of 4 from 8. This here would say more than a distance of 2 from 3. Well, think about that. Put 3 in here. So this phrase here would be a distance of more than 2, because greater than 2, from 3. Would you agree that just a number right to the right of 5, that first number to the right of 5, is more than 2 units from 3? And just this number right, 0.99999, is that number more than 2 from 3 on that side? And then all these other values have the same characteristic, same information. So now I want to convert these into interval notation. You've got to be careful with this, because you don't want to necessarily go straight from this to interval notation, because if I did this, it's going to be backwards. Remember, interval notation, we have to view it as we read our map or our graph, left to right. So if I'm reading my graph left to right, the first number that this bar comes in contact with would be negative infinity. As I move that bar through, the last important number, the last critical number that I come in contact with would be 1. And it's not really 1 because there's an open dot there, so I'm going to put a parenthesis here. Negative infinity belongs with a parenthesis. As my vertical line is through here, it's not intersecting anything, so there's no solutions in here. But the next number I can come in contact with is 5. But I don't really come in contact with 5. It's the immediate number after 5. So I put a parenthesis around 5. And the last number I would come in contact with, obviously this thing goes on forever, so it'd be infinity. Now I'm going to union those. And this is a number line. This left to right. This number, left to right, comes first before that one, which comes first before that one, and that one. They're in order. A lot of people that get these wrong do something like this. They'll say, oh, x is greater than 5, so they go 5 to infinity. Or x is less than 1. Oh, well, that means negative infinity to 1. It's the exact same intervals, but they'll union that way. And this is not chronological. Left to right, that number must be smaller than all these other numbers. And 5 is not smaller than that number or that number. So you got to be careful with that. Example. Just make sure my audio is still on. Okay. Example 5 here. I'm going to multiply both sides by, I'm going to isolate the absolute value. So multiply both sides by 3. So x minus 2 is less than 15. Okay. Now, it's a less than, so I'm going to give you this real quick. I'm going to show you kind of a alternative way of doing the less than problems if it makes it easier for you to learn the rule. we had said if f of x is less than c, then negative c is less than f of x is less than c. That's the rule. But that's an and statement. So I could write that instead. Negative c is less than f of x, and f of x is less than c, which would be that statement there. Now, most people don't appreciate this one here, this order, so they'll write f of x. We'll flip it. Let me put that back in there before I flip. So it'd be f of x is greater than negative c if I flip it. And then they still don't like that coming first, so they'll actually take this one and put it at the end here and say and f of x is greater than negative c. So here's the reason I'm writing it this way. So that says if the absolute value of f of x is less than c, then we get that argument right there. And that says exactly the same thing as this is saying. Why would I write it this way? Well, let's think about our other rule that said if f of x is greater than c, then f of x was greater than c, or f of x is less than negative c. You might like that. You might be a person that enjoys this a little bit better because what does this allow me to do? Well, it says if you have an absolute value is less than something, one portion of your solution is just going to be what I highlighted there without the absolute value bars. Is that the same thing right here? You just drop the absolute value bars and you get that. Then how do I get this part from what I started with? Well, that's the expression. You drop the absolute value bars, but now you flip the inequality sign and you negate your c term. So the same thing that happens here. Go from this yellow one right here to this. Did you drop the inequality sign, or sorry, the absolute value sign? Did you flip the inequality sign from what you started with? And did you negate c? So we think about the less than as an and statement instead of the between statement. That might help you memorize these two rules a little bit easier because they're very similar structures now. Okay, so it's up to you. That's an approach. I don't use that very often, but I do know some people appreciate that. I'm going to use the between statement. I think it's just so much easier to write negative 15 is less than x minus 2 is less than 15. Add 2 to both sides, or all three sides, or all three parts. So it gives me negative 13 is less than x is less than 17. And now negative 13 to 17. The only thing you would find out if you were doing this here instead, you would have like x minus 2 is less than 15. So then you would write x minus 2 is less than 15 and x minus 2 is greater than negative 15. So you can see that right there was that, and this one here is that. But now I'd have x is less than 17 and x is greater than negative 13. So now when I graph this, I got to remember what and means. And means the overlap. So I'd have x is less. So if this is 17, I would have x going there, and then x is greater than negative 13. So it'd be this stuff. If I was looking for the overlap, it'd be that. I'd have to be able to take it and rewrite it that way. The number one error that people see here is that they'll go from like negative infinity to 17 and then intersect that with negative 13 to positive infinity, which is it's true, but that is a more concise way of doing that is to rewrite this as negative 13 to 17. That's a better version of that there. Special cases. Okay. It's just like with special cases with absolute value. Like if I say absolute value of x plus 5 is equal to negative 10, there's no solution to that. And there's no solution to that because absolute value is a distance. If the distance of something is negative, that can't happen. Okay. So here, basically what we're saying is that the absolute value of x plus 1 is greater than negative 3 halves. Okay. So my question is, well, how often is the distance of something greater than a negative number? Isn't that always? Isn't distance always greater than negative numbers? So it'd be all real solutions. Another way of writing all real solutions or all real numbers in interval notation would be that. Okay. Here's another situation. I've always talked about graphing this stuff. Let's take a look at the graph here. If we go 2 times the absolute value of x plus 1, and then I have negative 3 as my y value, or my right-hand side. The question is, how often is 2x plus 1 greater than or above negative 3? Well, that red one is always above negative 3. That's why it's all real solutions. Okay, let's just do this next one graphically. Let's say absolute value of x minus 1 and y equals 0. How often is the absolute value of x minus 1 greater than or equal to 0? Well, the absolute value one is always above 0 or equal to 0. Okay, but what if I wrote it this way? What if I said, how often is x minus 1 greater than 0? Well, going back to the graph, it would not be at that point right there, because that's where they're equal. So I would, to answer, so this one here, again, would be all real numbers, but this one here would be negative infinity up to 1. That was the position that they were the same. Union 1 to infinity. Remember, that's the structure that we use to kick values out. I think we'll stop there for now.